this chapter on electric circuits where we focus on Kirchhoff's laws, resistance capacitance circuit, conversion of a galvanometer into an ammeter and into a voltmeter. One is the loop rule, the other is the junction rule. And according to the junction rule, the sum of the currents at a junction must be equal to 0. So A is an electrical junction, and at this junction you can see there are currents coming in and there are currents that are flowing out. So I1 is flowing into the junction, I2 and I3 are flowing away from the junction. And so if you take the sum of these currents, you must get 0. Now the currents flowing in are taken as positive and currents flowing out are taken as negative. So that means I1 is positive, so I1 minus I2 minus I3 is going to be 0. So that's how you apply the junction rule. But Kirchhoff's laws are basically an extension of Ohm's law. Now, Ohm's law can only be applied to simple circuits, but Kirchhoff's laws can be applied to complicated circuits. That means circuits having a number of branches or a number of loops. Let me illustrate that by using the simplest circuit that we can find, where you have a battery connected to a single resistance. So this battery sends current from the positive to the negative. So that's the direction in which current is flowing. And if we start from the positive of the battery and go in the direction of the current, the potential drop across the resistance is negative I times R. So whenever we go in the direction of the current through a resistor, the potential drop is going to be negative, the product of the current and the resistance. So it's negative I times R. But when we return, we are going from negative to the positive of the battery through the battery. And therefore, you take its voltage as positive. So when we write the equation, we get negative IR plus E is equal to 0, which when you rearrange becomes E is equal to I times R. And this is, of course, Ohm's law. Now, let's try to apply the same thing in this complicated circuit that we see, because this circuit has 3 loops. It has a top loop here, it has a bottom loop, and you can also take the outer loop. We will try to apply the loop rule to the 2 loops, the top and the bottom loop. But before that, notice that this current I1 is flowing into the junction. I2 and I3 are flowing away, just like we showed here. That's actually junction A, and this is our junction A here. So it's the same circuit. So when you try to apply the loop rule in the top loop, once again we start from the positive and go in the direction of the current. So the potential drop here will be negative I2 R1, because remember the current through this entire branch here is I2. So the current from here till here is I2, and that's why then the potential drop here is negative I2 R1. Why is it negative? Because we're going in the direction of the current. So it's negative I2 R1. Then come here, we're again going in the direction of the current. Once again, it's negative. So negative I1 R1. And then return, we are one more time going with the direction of the current. So it's negative I2 R2. But when we come to the cell, we're going from the negative to the positive. So it's plus the voltage of the battery. So that means the equation is negative I2 R1 minus I1 R1 minus I2 R2 plus E1 is equal to 0. Shall we try to apply this to the lower loop? This time we'll go even more slower so you understand. So let's start from the positive. Let's start from the positive of this battery and go in the direction of the current. So we're actually going in the direction of the current here because see, I3 is flowing this way, as you can see. I3 is flowing this way. So we're going in the direction of the current. So it's negative I3 R2, negative I3 R3, negative I1 R1 plus E2 is equal to 0. Again, so we start from here. So it's negative I3 R2, negative I3 R3, negative I1 R1 plus E2 is equal to 0. So that's what happens when you apply Kirchhoff's loop rule to the loop at the bottom. So once we get these equations, we will be able to solve the equations and then we can calculate the currents in different branches. So now let us try to actually apply Kirchhoff's law to a circuit and try to calculate the values of the unknown currents. So here is the circuit that is shown. This circuit has three currents again flowing. You can see I1 flowing here, I2 up and I3 down as before. I mean, it doesn't matter how you call the currents, you know. It doesn't even matter how we show the directions, because if we take the wrong direction, you're going to get the current as negative. So we're just using the same as before. And we will try to apply the junction rule here. And of course, that's going to give us I1 minus I2 minus I3 is equal to 0. We know that because I1 should be equal to I2 plus I3. So that's what we get when we apply the junction rule. But then when we apply the loop rule, we will apply it in the top loop. And we've done this before, but here are the values given. So when we start from the positive, from there and go in the direction of the current, the potential drop is going to be negative. It's going to be negative of the product of the current and the resistance. All right, so here it's going to be I2 times 0.5. And then when it comes here, it will be negative I1 R1. And here it will be negative I2 R2. And then since we're going from negative to positive, it'll be plus 18. So since we're going in the direction of current through all these three resistances, the potential drops are going to be negative. So let's write that down. So that's the important point to remember. If you go in the direction of the current, the potential drops will be negative. So all three are negative here because we decided to go in the direction of the current. And then when you come to the battery, you're going from the negative to the positive. That's why it's plus E1, see? And then I've substituted the values of the resistances, like R2 is 2.5, and voltage is 18, little r1 is 0.5, and caps R1 is 6. And then we see that there are two I2s. You see negative 2.5 I2 and you see negative 0.5 I2. You combine them to get negative 3 I2. So that's how we get that equation. Negative 3 I2 plus 18 minus 6 I1 is equal to 0. So now let's apply Kirchhoff's loop rule in the second loop. And in this case, just to show you the difference, I'm going to start from A and I'm going to go this way, clockwise. I'm going to go clockwise. Now, the reason is to show you that when we go clockwise, we are going against the flow of the current. Here, second case, and the third case. In all three resistors, we are going against the direction of the flow of current. That means the potential drops will be positive. You got it. If you go in the direction of the current, it's negative. If you go opposite to the flow of current, it will be positive. So that means in the second loop, we're going to get, that's the loop, A, E, F, G, H, A. You always end with what you start. You start with A, end with A to show that it's a closed loop. So that's why we get plus I1 R1. See, you're going against the current. And this is also plus I3 R3 plus I3 little r2. And then since we're going to the negative, you go minus E2 is equal to 0. And then plug in the values of the resistances. R1 is 6, R3 is 1.5, little r3 is 0.5, and the voltage is 45. And then again, there are two terms for I3, which is 1.5 I3 and 0.5. Combine that to get 2.0 I3. And then you can simplify these equations. I2 becomes 6 minus 2 I1. And from here, I3 is 22.5 minus 3 I1. That's because this whole thing is divided by 2. So if you divide this whole thing by 2, the whole equation, you're going to get this is I3, this is going to be 3 I1, and 45 divided by 2 is 22.5, and then you rearrange. So that's why we get those two equations. Now combined with that, we know that I1 is I2 plus I3. So we can use that to substitute for I1. I1 is I2. Since we know I2 is 6 minus 2 I1, we just go I1 is 6 minus 2 I1 plus I3. And I3 is this whole thing. So you have I2 and I3 here. And if you add them, you should get I1, correct? So I'm going to add the right-hand sides of these two equations to get I1. And that means that equation only has I1 in it. So if you do the algebra, you will get I1 as 4.75 ampere. And once you get I1, we can get I2 because I2 is 6 minus 2 I1. So 6 minus 2 times the value of I1 will give you negative 3.50 ampere. And then we can find I3 either by substituting into this equation or using any other equation. Now notice that for I2 we got negative 3.5, which means the imagined direction of current is not correct. Actually the current was flowing down. So that doesn't matter. So you can actually imagine the current to be flowing in any direction. If you get it as negative, that means your imagined direction was not correct. So this is how we apply Kirchhoff's junction rule and the loop rule to calculate the values of the unknown currents. So we got to get as many equations as the number of unknowns. So if you have 3 unknowns, as in this case, I1, I2, and I3, then we need to at least get 3 equations. And then we solve those 3 equations to find the values of the unknown currents. Next, we want to look at 2 important measuring instruments. One is the voltmeter, the other is the ammeter. Let's start with the voltmeter. A voltmeter is used to measure an unknown voltage. It's used to measure the unknown voltage across a resistor. So whenever a voltmeter is used, it has to be connected in parallel to the resistor or to whatever you're trying to find the voltage across. In short, the voltmeter must always be connected in parallel. So you can see that to measure the voltage here, you got to to connect the voltmeter in parallel. Same in these 2 cases. And when you try to measure the voltage of a source, the internal resistance of the source is also going to be included in the. Next, we have the ammeter. The ammeter is used to measure currents, and therefore it has to be connected in series with the circuit, because the same current should flow through the instrument. So that's why the ammeter here is connected in series, not in parallel. So you know that the current that flows through this entire circuit is going to be the same, and so that flows through the ammeter. So an ammeter is always connected in series in a circuit, and it doesn't matter where the ammeter is connected. It could be placed here, it could have been placed here, or it could have been placed here. Since the current in the circuit in a series circuit is the same throughout, you can place the ammeter where. The galvanometer is a very sensitive instrument. The galvanometer is a detective. It's used to detect even a minute current in a circuit. Therefore, it cannot really be used as a measuring instrument. It can only be used to detect. But if we want to use it as a measuring instrument, we need to change it into a voltmeter or into an ammeter. Now, in order to change the galvanometer into a voltmeter, a high resistance must be connected in series with it. As you can see in the diagram, when this galvanometer, which has a small resistance, a galvanometer has an internal resistance that's very small. If you want to use this as a voltmeter, you've got to connect a very high resistance in series with it. And we can find the value of that resistance to be connected. And to find the value of the resistance to be connected, we should know that the current I sub G is what's flowing through this entire path. So when it flows through that path, the total resistance of the path is R plus R. And so when you multiply IG times R plus R, we must get the voltage to be measured. So that's the idea, simple application of Ohm's law. So IG multiplied by R plus R must give you the voltage. Now from this equation, we can rearrange, use the math to make caps R the subject. And we would get the formula as V by IG minus R. So that gives us an equation to calculate the high resistance that must be connected in series with the galvanometer. And the value of the resistance depends on how much voltage we want to measure. I'm going to give an example here. So let's assume that IG is 1 milliampere. Usually it's very small. 1 milliampere is 1 by 1,000th of an ampere, and that is the maximum safe current through a galvanometer. Okay, so let's take IG as 1 milliampere, and assuming that we want to measure a voltage of 10 volt and that the internal resistance of the galvanometer is 10 ohms, the value of the resistance connected would be 10 divided by 0.001, because 1 milliampere is 1 by 1,000, so that's 0.001. Minus 10, which comes out to be 9,900 ohms. 10 by 1,000, 10,000 minus 90, so that should actually be 9,990 ohms. Okay, so I see the mistake there. 9,990 ohms must be connected in series to this galvanometer to convert it into a voltmeter, a galvanometer into an ammeter. Now it's exactly the opposite of what we did before. To convert it into an ammeter, we have to connect a really small resistance in parallel to the galvanometer. So we can see that this is the galvanometer shown with its internal resistance, and we have to connect a real small resistance, but this time in parallel with it, and then this whole thing is now an ammeter. Okay, and we can again find out the value of the resistance to be connected by looking at the circuit carefully. See that the total current comes in and divides into two parts. One part, Ig, goes through the galvanometer, and the current I flows through the resistance. When you add I and Ig, we must get the total current, because it's the total current that splits into two. So we can calculate the voltage between these 2 points in 2 ways. The voltage can either be I2 multiplied by little r, or I multiplied by caps R. Because the voltage in parallel branches are equal. So the voltages here and here must be equal. So that's the idea. So we get Ig multiplied by little r is I times caps R. And then rearrange that. And you get that formula. But remember that I total is Ig plus I. Or I is I total minus Ig. So substitute the value of I here, and then we get the formula. So here is an example. Again, let's consider that Ig is 1 milliampere. The internal resistance of the galvanometer is 10 ohms. And we got to find the resistance to be connected in parallel. And we have to decide up to what current you want to measure. Let's assume that we want to measure up to 10 ampere. Okay, so that's I total. 10 ampere is the current that should come into the ammeter. So first of all, I is I total minus Ig. So that's 10 minus 0.001, because 1 milliampere is 0.001. And then plug it into the formula, and you see that the value of the resistance is extremely small. It comes out to be 0.001 ohms approximately. So that's how a galvanometer is converted into an ammeter. Next, we need to talk about bridge circuits. You know, bridge circuits are used to basically measure an unknown resistance. It can also be used to measure an unknown capacitance. And we're going to do both of these labs. So this is an important circuit. Essentially, what a bridge circuit is 4 resistances are connected as shown in the diagram. And the arrow here shows that that's a variable resistance. You can change it. And then a galvanometer is connected with a switch. And again, there is a power source, there's a battery connected. So that's a bridge circuit. In the bridge circuit, after the switch is closed, the value of the resistance here, which is R3, is changed. R3 is changed until the galvanometer shows 0. That means no current is flowing through the galvanometer, or Ig is equal to 0. In this case, the bridge is said to be balanced, or this is called a null deflection method. Now, null deflection means zero deflection method. So when we do this lab, we will adjust the value of one of the resistors so that the galvanometer shows absolutely no deflection. So in a balanced bridge, we can apply Kirchhoff's loop rule. So you see this loop here. You can apply Kirchhoff's loop rule, and we can see the equation that we get. So it's all under the condition that Ig is 0 or the bridge is balanced. So then I2 times R3 should be equal to I1 times R1. Why? Because there's no current through the galvanometer. These two potentials have to be equal. Or if you start going in the direction of the current, here you would go negative I1 R1. Here there is nothing. And you would go negative. You're going against the current, so you go positive I2 R3 is equal to 0. All right. Negative I1 R1, positive I2 R3 is equal to 0, which is the same as I2 R3 is I1 R1. All right, and then we can do the same in the other loop. In the other loop, again, the products must be equal. So that means I2 times Rx. Rx is the unknown resistance, is I1 R2. And now if you divide the left side by the left side, the I2s cancel out. On the right side, I1s cancel out, and we are left with a ratio from which we can find the unknown resistance Rx, knowing the values of the other three resistances. So that is the bridge method to find an unknown resistance. Resistance capacitance circuit, or the RC circuit. Whenever you charge a capacitor, it cannot be directly connected to a battery, because then the charging will be instantaneous and the capacitor will blow up. So usually the capacitor is connected to the battery via a high resistance. So as shown in the circuit, this capacitor is going to be charged using this battery, but through a high resistance. And when the capacitor gets completely charged, you see the positive charge is on this upper plate because it's connected to the positive, and the negative charge is on the bottom plate. When the capacitor is fully charged, we know that it has taken a certain time to reach that. And this charging is always exponential, as you can see from the graph given here. So here you have time, and on the y-axis you have voltage. Now voltage on the capacitor increases with the charge. So it's exponential, it's an exponential increase. As you can see, it increases there, and it's given by a formula that is the voltage at any time is the maximum voltage multiplied by 1 minus e raised to minus t by RC. Now, R times C is called the time constant of the circuit. Time constant of the circuit. So if you take the values of the resistance and the capacitance and multiply it, you will get the time constant. And since charge is the product of capacitance and voltage, we have a similar equation for charging of the capacitor, which is Q is equal to Q naught 1 minus e raised to minus t by CR. You will understand the full impact of this equation when I work out a problem later on. But then there's another method, there's another equation rather, for discharge of a capacitor through a resistance. So this capacitor is now fully charged, and next we're going to connect it to a resistor, and the capacitor is going to discharge. So the process is now opposite. So in the beginning, the charge is maximum, and then the charge exponentially decreases to 0. Okay, so that's what is shown in this circuit. So now you do not have the battery, you have a fully charged capacitor, and it's going to send current in this direction because the top plate is positive and the bottom is negative. And it's an exponential decay or exponential discharge, and the formula is slightly different. You can see the difference. There's no 1 in the equation. So the voltage would be, I didn't write the voltage equation here. I'm going to write it. The voltage equation is I've written the equation for the charge, and the equation for voltage is similar, and it's Q is equal to Q naught e raised to minus t by CR. So you see that it's slightly different. So depending on the problem, you have to use the correct equation. If it's asking you for discharge, use this equation. And there are so many practical applications of this resistance capacitance circuit, but one that we see in daily life is the turn signal indicator in a car. You see, when you have to turn left or right, you see the blinking lights, and the lights blink with a certain frequency, with a certain time period. And that happens because of a resistance capacitance circuit. So here is the circuit. You have the light bulb, the indicator, okay, the light bulb, which usually has a very high resistance. And so here is a capacitor, and the capacitance is going to get charged. No current will flow through the light bulb when the capacitor is charging, because the light bulb has a very high resistance. So now the capacitor gets charged, and once the capacitor gets charged, it wants to discharge, and it cannot discharge through the battery because the battery is trying to keep sending a current, and it's impossible for the capacitor to send a current in the opposite direction. So the low resistance path is now the light bulb. Therefore, the capacitor discharges through the light bulb, and that's when you see the lights come on. And once the light bulb is once the capacitor is completely discharged, the process is repeated. Again, the capacitor gets charged. Once again, it discharges. So you see the graph. First, it gets charged, and then that's a discharge. Then again, it gets charged, and then that's a discharge. So there is a continuous process, and that happens with a certain time because the RC circuit has a time constant. Remember, the time constant is the product of the resistance and the capacitance. So finally, here is a problem, and the capacitance is 1 microfarad, and we got to find the charge after 1 second of charging using a source of 6 volt. So the values of the resistance and the capacitance are given, and we have to find the charge on the capacitor during charging. It's after 1 second of charging. So the time is 1 second, and the source voltage is 6 volt. The first thing we got to do is find the maximum charge that is going to be on the capacitor. How do we know the maximum charge? The charge on a capacitor is the product of the capacitance and the voltage. So when you multiply 1 microfarad with 6, we are going to get the maximum charge on the capacitor. Here is the formula that we're going to use, but we need the maximum charge in the capacitor, which is Q naught. And so we find that first. And remember to change microfarad into farad. Micro is 10 to the negative 6. So we get 6 times 10 to the negative 6 volt. Once you get that, just plug it into this equation. And you have 1 minus e raised to negative 1 by R times C. So R is 1000 kilo ohms. A kilo is 1000. So you have 1000 times 1000, which is 10 to the power 6. And then a micro is 10 to the negative 6. So that's why I have those numbers for R and C. And that product becomes what? 10 to the 6 multiplied by 10 to the negative 6 is simply 1. So in the next step, you're going to see that happen. It's 1 minus e raised to, e raised to negative 1. And so now in the calculator, you try to find the value of that. That's to make a correction there. It's 1 minus e raised to negative 1. And put this into the calculator. 1 raised to negative, e raised to negative 1 is 0.368. And then 1 minus 0.368 is 0.632. And so you multiply that and you get 3.79 times 10 to the negative 6 coulombs. So that will be the charge on the capacitor 1 second after charging begins. So I hope you understood both parts 1 and 2 of this chapter. This is a really important chapter, and I hope you continue watching these videos to study the subject of electrical circuits, which is awesome, amazing, very interesting. Thank you.